Unit 1A, Lesson 2. This lesson will align with 5.4 in your textbooks. The one standard we are going to discuss in this lesson: solve quadratic equations with real coefficients that have complex solutions. The key vocabulary in this lesson: quadratic equation. The general form for a quadratic equation is ax squared plus bx plus c. The next term is real numbers. We discussed this in the last lesson. A real number is any number that doesn't involve the letter I, which stands for an imaginary number. And then we have coefficients. If we have term 7x, the coefficient is the number in front of the variable, making sure you understand all three of those terms throughout this lesson. First few examples, we want to solve each quadratic equation by finding square roots. We use this method if we're missing the middle term. So we have 2x squared minus 16 equals 0. We have no x term, so we're going to use the square roots method. If we're trying to solve this quadratic equation, we need to isolate our variable. The first thing we're going to do, add 16 to the other side. We're left with 2x squared is equal to 16. Next thing, to get x squared isolated by itself, divide by 2. We're left with x squared is equal to 8. And now we need to get rid of that squared on the variable, so we take the square root of each side. We're left with x is equal to, when we take the square root over the variable, we have to account for the positive and the negative. So we have plus or minus radical 8, which we can break down to plus or minus radical 8 is the same as the square root of 4 times the square root of 2. We know the square root of 4 is 2, so this is plus or minus 2 radical 2. That's using the square roots method. Next example, we want to solve the quadratic equation by using the quadratic formula. Recall from Algebra 1, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2 times a. A, recall, is the coefficient in front of x squared, b is the coefficient in front of the x term, and c is the constant, the number by itself without a variable. In this problem, we have x squared minus 8x plus 12 equals 0. Thus, our a value is 1, the b value is negative 8, and the c value is 12. All we need to do is plug these values into that formula and simplify. So we have x is equal to the opposite of b. The opposite of negative 8 is a positive 8, plus or minus the square root of negative 8 squared minus 4 times our a value is 1 times the c value is 12. And that's all divided by 2 times our a value, which is 1. Simplifying, we have 8 plus or minus negative 8 squared is 64. 64 minus 48. So we have 64 minus 48 is going to leave us with the square root of 16 divided by 2. We know the square root of 16 simplifies down to 4, so we have 8 plus or minus 4 divided by 2. 8 plus 4 is 12. 12 divided by 2 is 6. 8 minus 4 is 4. 4 divided by 2 is 2. So using the quadratic formula, we go through, identify a, b, and c, plug those values in, simplify. Our solutions are going to be 6 and 2. We could have also used factoring to solve this problem. If we go down below and just look at this, we want to look at factors of 12 that when we add together give us negative 8. Well, we know negative 6 times negative 2 is going to give us positive 12, And if we add -6 and -2, that's going to give us -8. So we could have factored this into x minus 6 times x minus 2 and set that equal to 0. Once we have it in factored form, we can use the zero product property, set each of those equal to 0, each of those factors. So x minus 6 equals 0. If we solve that, we get x equals 6. If we set x minus 2 equal to 0, we get x equals 2. A couple different methods we could have used to solve this problem. So in the previous example, we used the finding square roots method. In this example, we used the quadratic formula and factoring, going through all those processes. The other two processes we have for solving quadratic equations, we could graph and look where the graph crosses the x-axis, or we could use completing the square. And we'll go through those other two, graphing and completing the square, at a different time. Next, we are going to discuss the discriminant. If you look, we have the quadratic formula, x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2 times a. The portion underneath the radical sign, b squared minus 4ac, that's called the discriminant. It has a special purpose because it allows us to determine how many real solutions there are to a quadratic equation. If we take the discriminant and that value is greater than 0, that implies there are 2 real solutions to the quadratic equation. If we take the discriminant and it equals 0, that implies there is 1 real solution to the quadratic equation. And if we take the discriminant and that value is less than 0, that implies there are no real solutions to that quadratic equation. Now we're going to use the discriminant to determine the number and type of solutions. In the first example, we have 2x squared plus 3x minus 7 equals 0. Identify what the a, b, and c values are. A is equal to 2, b is equal to 3, and c is equal to -7. Now we plug these values into the discriminant, b squared minus 4ac. So we have 3 squared minus 4 times the a value, which is 2, times the c value, which is -7. So we have 3 squared, which is 9. -4 times 2 is -8. -8 times -7 is a positive 56. So we have 9 plus 56, which is going to be 65. 65 is greater than 0. So since the discriminant is greater than 0, we have 2 solutions, and more specifically, we have 2 real solutions. In this next example, we have 4x squared plus 18 equals 0. We need to identify what the a, b, and c values are. A is equal to 4. There's no middle term. There's no x term. That means our b value is 0, and c is equal to 18. Plugging these into the discriminant, b squared minus 4ac, we have 0 squared minus 4 times the a value, which is 4, times the c value, which is 18. -4 times 4 is -16. -16 times 18 is -288. Thus, the value of our discriminant is less than 0. That implies there are no real solutions to this quadratic equation. If we would graph this quadratic equation, since there's no real solutions, that means this quadratic equation, if we look at the graph, it's never going to cross the x-axis. There will be no x-intercepts. The last main idea for this lesson is the complex conjugate theorem. This theorem says if a polynomial has real coefficients and a plus bi is a solution, then a minus bi must also be a solution. Complex solutions occur in conjugate pairs. In this example, given one root of the polynomial, find the other. First example, we have x squared plus 3025 equals 0. We know that one solution is 55i. So as long as we have a polynomial with real number coefficients, which we do, if we know we have one complex solution, 55i, there will also be the complex conjugate to that is also a solution. That's what the complex conjugate theorem says. We want to think of 55i, that's the same as 0 plus 55i, which means the complex conjugate of that is 0 minus 55i, which means negative 55i will also be a solution to this polynomial. The second example, we have x squared plus 158x plus 14,890 equals 0. We're told one of the solutions is negative 79 minus 93i. All the coefficients are real numbers. We're told one of the solutions, and that's a complex solution. Complex solutions occur in conjugate pairs, which means negative 79 plus 93i must also be a solution. We started with a quadratic. We know there's two solutions. We have both solutions. So again, the complex conjugate theorem, as long as we have a polynomial with real number coefficients, if we have one solution that is a complex number, there must be a conjugate pair that will also be a solution. In this last example, we want to write a polynomial of least degree with real coefficients and the given roots. We're told that 2 plus I is one root to the polynomial, which implies that there must be a complex conjugate that is also a solution. The complex conjugate would be 2 minus I. So now we want to write the polynomial. If these are the two solutions, that means we can write x minus 2 plus I, and we can write x minus 2 minus I. If these are the solutions, this is how we write them in factored form, x minus that solution. Rearranging this a little bit, this is the same as x minus 2 plus I, and this would be the same as x minus 2 minus I. The reason I'm going to do that is now we can FOIL. We're going to treat this as one term. We're going to treat this as one term. So if we FOIL this out, multiply the first, we're going to get x minus 2 quantity squared. Now if we multiply the outsides, this is going to be minus the quantity of x minus 2 times I. If we multiply the inside, this is going to be plus the quantity of x minus 2 times I. And then we're taking I times I, so this will be I squared. If you look at these middle terms, okay, it's a little complicated, but we have the quantity x minus 2 times I, we have a negative and a positive. So these two middle terms are going to cancel each other out. So what we're really left with right now is the quantity of x minus 2 squared. We talked earlier, I squared is equal to negative 1, so if we're subtracting negative 1, this is actually plus 1. Rewriting this, x minus 2 quantity squared, we can write that as x minus 2 times x minus 2 to make this a little easier to multiply out. Again, using the FOIL method, x times x, we're going to get x squared minus 2x minus 2x minus 4x plus 4 plus 1. Combine like terms, we get x squared minus 4x plus 5. This is a polynomial of least degree that we can write given that 2 plus I was a solution, and then we had to determine that 2 minus I would also be a solution. So given these two solutions, We can write them in factored form, multiply out using a little creativity to come up with a polynomial that seems pretty easy to work with, x squared minus 4x plus 5. In this lesson, we reviewed many methods to solving quadratic equations. We talked about the discriminant and how we can use it to find the number of real solutions to a quadratic equation. Then we talked about the complex conjugate theorem. If we have polynomial with real number coefficients, if there is one complex solution, we know there must also be a complex conjugate that is also going to be a solution. In class, we're going to work more with solving quadratic equations using those methods we talked about to solve quadratics that have complex solutions.